All right, so yesterday we started looking at unit circle trig, and remember that the real kind of overall goal of unit circle trig is to give you a quick way to deal with angles that are 30 and multiples of 30 and 45 in your head. Okay, to be able to figure out all 6 trig functions for anything that's a multiple of 30 and 45. The easiest ones are the quadrantal angles. Okay, those are all multiples of 90, which includes 30s and 45s. The nice thing about those coordinates is they don't have any fractions. All the coordinates have are zeros, ones, and negative ones. When we started to look at the coordinates for the 45, that's the one we did yesterday, we saw that we get fractions and we get square roots. Okay, that adds a couple things we need to do. One, you can't leave a fraction over a fraction, so we have to simplify that. And where are you not allowed to leave a root? Yep.
In the bottom.
Right, in the bottom. So that's something else we need to fix. Both of those things are going to come up when we do the 30 and when we do the 60. Okay, we're going to have fractions and we're going to have roots. All right, so we did the 45, 45. Let's look at the 30, 60, 90. So that triangle would have come from having a circle, putting a dot at the 30-degree mark, and then creating a triangle out of that. Drawing a hypotenuse and drawing a perpendicular to the horizontal. Okay, I've drawn that triangle bigger off to the side so we can work with it. The right angle is in the lower right. And because the hypotenuse is pointing at 30 degrees, that means this angle right here is the 30, and this one at the top is a 60. How come the one at the top has to be a 60? If we know that that's a 90 and a 30.
Triangle has to add up to 180.
Right. A triangle has to add up to 180. So now we want to figure out the sides in that triangle. Yeah?
I was gonna say the one on the right does not match the one on the left because the 60 is not in the same place. And
The 30 is on the outside of the triangle.
yes,
there.
but
Yeah.
it's not the correct side. No, that's the thing.
So that's your 30. And that angle right there is your 60.
And then what's the other 30 doing?
That's on the outside of
Oh,
the,
okay.
that's like on the unit circle marking,
Oh.
like if this is 0, that's 30, 90, 180, 270. It's
Okay,
just the
then.
30-degree mark on the circle. Yeah. Any other question on that? That's important to understand. Okay. So the 30 on the outside, that's just marking the position going around the circle. When I make the actual triangle, the 30 is tucked in towards the origin, the 60 is up at the top, and the 90 is at the bottom. Okay. So is there any sides that we already know in that triangle?
The hypotenuse.
Yeah. How long is the hypotenuse?
1 unit.
1 unit. All right. Now, yesterday we used Pythagorean theorem to get the other 2 sides we were missing. What's different about this triangle than the one we did yesterday? Yeah.
The other 2 sides aren't the same.
Right, the other 2 sides aren't the same. So if you want to use Pythagorean theorem, you'd have to pick 2 different letters. And then if you pick 2 letters, how are you going to solve that? Because you can only have 1 letter. All right, so what that means is we can still use Pythagorean theorem, but we have to figure out one of the other sides first, somehow, a different way. Okay. And what I'm going to do is give you a hint at how you can do it. I'm going to go like that. Okay. So, anybody have any thoughts how I'm going to figure out another side in that triangle, but not using Pythagorean theorem yet? Yep.
There's the 30, 60, 90 right triangle.
So yes,
sides theorem. I forget what it's called.
if you had that memorized, yep, you could use that. I'm gonna bet there's some people that don't remember the relationship between all the sides in a 30, 60, 90.
I believe the side on the right is 1/2, and then the one below is square root of 3/2.
Yes, that's exactly what it is. In case you don't know that though, we're gonna figure out what those two numbers are, but you are exactly right. Yeah. So does anyone know how we can figure out those two numbers? Yeah,
For the side lengths, is that
this is a big hint.
Alright. So, can't you use sine of 30 and then also cosine of 30 to find the opposite and adjacent angles?
We don't know, or I haven't taught you trig yet, so we don't know how to do that in general.
Someone else has though.
Somebody else might have to do it. So these are all great ideas, assuming you have prior knowledge of those ideas. But we're going to try to figure out the two side lengths here, and you're not going to have to know anything prior to do this. Well, you won't have to know anything that would be above the level of knowledge I've taught you. You'll know things from geometry, but not above trig.
Just looking at the side lengths, wouldn't it technically be like if the longest length is the 90-degree angle, wouldn't the second longest be roughly 2/3 of it with the 60 and then 1/3 with the 30 as it decreases in angle length?
So it's a good idea to think of that way, but it's not a linear relationship between the size of the angle and the length of the side. Just because you double the size of an angle, it doesn't mean that the length of the side across from it doubles. If it did, it would be directly proportional, but it's not. So something I can do with these two triangles. Yep.
So is the hypotenuse 1 here?
Yeah, the hypotenuse is 1. Yep.
We can't use like the opposite over adjacent sine of 90?
If people knew SOHCAHTOA, then yes, you could. Yeah. But I'm not sure everybody knows or remembers that. So I'm trying to think of a way to figure out these two sides without depending on something people might not remember. But yeah, all very good ideas. That would work. Yes.
This is kind of a long shot, but do you make a rectangle out of the two of them?
Okay, you do want to make another shape, yes, out of the two of them. A rectangle is often suggested to me, but it's not a rectangle. But a lot of times people do suggest that. What else could we make? Yeah.
Another triangle.
Okay. There's a couple ways I could do that. I'm looking for a very specific one.
Specifically, isosceles.
I don't want to make an isosceles triangle. Does anybody see another type of triangle I could make?
Hey,
Yeah.
the 60-60-60
How could I make a 60-60-60?
by putting the bottom end of both triangles together.
Okay.
So you flip that one over, and then you attach them on that side, so it's both right angles next to each other. And then the 230s add up to 60.
Okay.
And now you have all three equal sides.
So now we have three equal sides, yeah. So this side, that side, and that side are all one, because that's an equilateral triangle.
No.
And what do we know about how, we'll call it the green side, compares to the blue side?
It's even.
Even? Oh, yeah, equal, right? Yeah, they are equal, exactly. And we know that it's 1 unit from here to here, because that's an equilateral triangle.
Yeah,
So what does that tell us?
it's 1/2.
Right. So that automatically tells us that that side is 1/2. We don't need the bottom triangle anymore. Right? We just figured out one of the sides we didn't know by just kind of doing a clever trick of putting the two together and knowing the two sides we put together are congruent. And if two numbers are the same and add up to 1, the only option is 1/2 and 1/2. Okay. So any question on how we got the 1/2? And that didn't depend on any trig. It depended on some geometry, but nothing that we haven't learned before this class. All right, so now that I've got that, I'm going to move the bottom one out of the way. And I still don't know the bottom side, but what could I call the bottom side now? Yep.
X or any
Sure.
other variable.
Now we can just call the bottom side x. And what theorem can we use to figure out the bottom side now?
good guy, Pythagorean.
Yeah, we can use the Pythagorean theorem. Okay. Why can we use it now but we couldn't before? Oh, wait.
Because we only had one side.
Yeah, we only had one side before. Now we've got two. So once you got two, Pythagorean theorem is perfect. Joe, can you set up my Pythagorean theorem for me using those three numbers?
1
Half squared
squared plus x squared plus x squared.
plus x squared. So we're going to get 1 equals a quarter plus x squared. What does x squared equal? Yep,
3/4.
3/4. And we talked about that yesterday. When you take a square root of each side, you take the square root of the top and the bottom. So if you solve that for x, what will you get? Yeah,
Square root of 3 over 2.
perfect. Square root of 3 over 2. All right. So now, if we go back up to our picture, we know that this bottom side is root 3 over 2. And we know that the short side is 1/2. So let's put it together. What would be the coordinate to get to 30 degrees? How far to the right? And then how far up do you have to go? Yep.
Square root of 3, 1/2.
Square root of 3, 1/2.
Sorry, square root of 3 over 2.
Square root of 3 over 2, 1/2. And that is the coordinate for 30 degrees. Square root 3 over 2, 1/2. Okay, now, let's look at the 60. The diagram's getting a little crowded, so I'm gonna draw it again with just the 30 and the 60 and not all the other labels. So here's your 30. Here's your 60. The 30 is the triangle we just figured out. The 60 is the one I want to do now. Does anybody notice anything about the red triangle and the black triangle? Yeah.
They're exactly the same, just in different positions.
Right, they are congruent. Right? They are exactly the same triangle. Okay. The difference between the red and the black one is kind of laying down on the long side, the long leg, and the red one is standing on the short leg. So we know this is root 3 over 2, 1/2. The red is the same triangle, just oriented a different way. So what do you think the coordinate would be for 60? Yep, Waylon?
1/2 root 3 over 2.
Yeah. 1/2 root 3 over 2. And the way that you can remember which one comes first is if you imagine drawing it. 1/2 as a decimal is what number? 0.5. Root 3 over 2 is 0.866. That one that I'm pointing to is a bigger number. The bigger number always goes with the long side. The smaller number goes with the short side. So this is the long side. It gets the big number. That's the short side. It gets the small number. Okay, the short side is always going to be across from the smallest angle. Smallest side, smallest angle. Bigger leg, bigger angle. All right, so the 30, the side across from the 30 is always the shorter side, and that's the 1/2. The side across from the 60 is always the long side. That's the root 3 over 2. So let's say I wanted to draw a multiple of 30. Let's do 150. First, can somebody tell me what quadrant 150 would be in?
2.
It would be in quadrant 2. And there's really three options for where it would be. Is it right in the middle, closer to 90, or closer to 180? Where's 150? Yeah,
Close to
it's closer to 180. So we're going to draw it somewhere around there. If you draw it somewhat accurately, you should be able to tell which side is the long side and which side is the short side. I make them different colors. Which side is the long side there? Which one?
Blue.
Blue, yeah, that's the long side. Let me write it in black. And which side is the short side? Yep, green. Now, when you write your coordinate for 150 degrees, we just have to be careful because something happens in quadrant 2 that doesn't happen in quadrant 1. What happens when you write a coordinate and it's in quadrant 2? Yep. The root 3 over 2 is going to be negative. Yep. So the coordinate for 150 is negative root 3 over 2, positive a half. So now we know how to, well, we should know how to do 12 different angles that are all multiples of 30 and 60. 2 in the first quadrant. You got your 2 in the second quadrant. You got 2 in the third quadrant. And then you have 2 in the fourth quadrant. Kind of like, oops. Sorry, I didn't draw it. Should have drawn with my tool that makes perfectly straight lines.
No, it's fine.
But so you get the idea. So there's 2 in every quadrant. And then you add the 45s in, which I'm not going to do on this diagram, but that gives you a third one in each quadrant. So there's 12 different angles that we can do on the unit circle that are multiples of 30 or 45. And then we also have the ones that are right on the axes, 0, 90, 180, and 270. So that's 16 different points that we can do on the circle. And I can ask you for any one of the 6 trig functions of those 16 different points. So now we'll practice some of those. Okay. So any question on the coordinates for the 30 or the 60? All right. So we did that yesterday. That was the 45. Someone just remind me, what's the coordinate for 45? Joe? Root 2 over 2, comma, root 2 over 2. Yep. So there's only 3 numbers you have to remember to do everything in unit circle trig that's not on an axis. Root 2 over 2, root 3 over 2, and a half. Those are the 3 numbers that will keep coming up. All right. So let's do the 6 trig functions of 30 degrees. What's the first thing that we would need to know if we're going to do the 6 trig functions of 30 degrees? What do we have to know?
The coordinate for 30 degrees.
Yep,
Which is
we need the coordinate for 30 degrees, which, can somebody remind me how we're going to calculate that coordinate? Well, Bella, how are we going to calculate the coordinate for 30 degrees?
You gotta memorize it.
We got to memorize it. We are not going to calculate it, right? We don't want to go through all that again. Can you tell me what the coordinate for 30 degrees is?
Square root of 3 over 2 and 1/2.
Yep.
Comma 1.
So when you do 30, that's closer to the x-axis. That means the long side is horizontal and the short side is vertical. So it's root 3 over 2, 1/2. All right, now we'll go through all 6. What is the sine of 30 degrees? Yeah, right? Yep, 1/2. Okay, what's the cosine of 30 degrees? Root 3 over 2. And now the tangent of 30 degrees, you're going to divide y by x, if you imagine putting a division line right there, what cancels out right away when you divide? Yep, the 2's. So you're left with 1 divided by root 3. But we need to fix that so we don't have the square root in the bottom. What does that turn into? Yep.
It turned into square root of 3 over 3.
Square root of 3 over 3. Perfect. Okay. How about my cosecant of 30 degrees? What's my cosecant? Yep. 2. Okay. How about the secant of 30 degrees? Final answer. Fully everything you need to do to fix it. Yeah.
2 over 3.
Yep, 2 root 3 over 3. And how about the cotangent of 30 degrees? Yep,
Root 3.
root 3. Okay, when you get to this one, you have 2 things you could flip. You could flip the first one or the second one. I would flip the first one because the square root's in the bottom, and if you flip it, it goes to the top. If you flip the second one, you're going to get the same thing, but then you got to fix it because you put the root back in the bottom all over again. Okay. So there's your 6 trig functions of 30. Let's do 60. All right. What's the coordinate for 60 degrees? Yeah.
1/2 square root of 3.
Yes. So 60 degrees, now you're visualizing a point that's higher up on the circle. So it's higher, so the y value is the big one. Okay, what's my sign? Yeah,
Root 3 over 2.
root 3 over 2. Okay, someone else, my cosine? Yeah, 1/2. Okay, my tangent? Again, just imagine putting a division line right there and dividing what you have left. Well, Nick? Yep, the 2's are going to cancel and you're left with just root 3. And now, just flip them all. So 2 root 3 over 3, 2. And what do you get when you flip root 3?
Root 3 over 3.
Yes. Okay. So that's your 6 trig functions of 60. If you compare it to 30, you get all the same numbers. They're just in different spots. Look carefully at which ones switched places. These 2 switched. These 2 switched. And those 2 switched. What I just grouped together are called cofunctions. A cofunction is when you take a trig function and you put the word co in front of it. Sine, cosine. Tangent, cotangent. Secant, cosecant. That's a little bit different pairing than reciprocals. Reciprocals are straight across from each other. Those, the blue ones, the red ones, and the green box, those are called cofunctions. And we'll talk more about what that means later on. But for now, if you just notice those are the ones that switched places from the problem on the left to the right, that's good. Okay, let's try the trig functions of 135. When the angle is not a 0, 90, 180, or I'm sorry, when the angle is, when it's not 0, 90, 180, or 270, you have to figure out if it's a multiple of 30 or 45. Well, I'll give you a hint. A multiple of 30 never ends in a 5. So that kind of gives it away which one this is. What we want to try to do is draw this picture in our head. If you imagine a unit circle, first think about the quadrant 135 is in. What quadrant is it in? Yep.
Quadrant 2.
Quadrant 2. Let's make sure we know our quadrants. So quadrant 2. You have 3 places it could be. It's not on an axis because it's not 90 and it's not 180. It's in a quadrant. It's either right in the middle, closer to 90, or closer to 180. Where's 135? Yep, it's right in the middle. Because it's right in the middle, what kind of triangle is that I just drew? Based on the angles, if you were to label them all. Yeah,
45?
that's the 45, 45, 90. So when you draw the 45, 45, 90, that's where we need to memorize what the two lengths of the sides are. What is the length of each side in a 45, 45, 90? I don't care about direction yet. I just care how long is each side. That's not the hypotenuse. Yeah.
Each side is root 2 over 2.
Root 2 over 2. Root 2 over 2. Now I care about direction. What would be the coordinate for 135 degrees? And just make sure you take into account you're going left and then up. Yep.
Negative root 2 over 2, and then 2 over root 2 over 2.
Perfect. Okay. They're not asking for all 6 here. They're just asking for the first 3. We've done enough with all 6. We're just going to start doing 1 now. Like it'll be on the test. Okay. So what's the sine of 135? Yep.
Or 2 over 2.
Root 2 over 2. Okay. What's the cosine of 135? Yep.
Would it be negative root 2 over 2?
Right. So the coordinate, you got to get the x value, and the x value, there is a negative. I know it's kind of small, but there is a negative there. Okay, so it's negative root 2 over 2. And what about my tangent? Yep. Right. We're dividing two numbers that are opposites. When you divide opposites, you get negative 1. And that's the first 3 trig functions for 135. Any questions on that? Okay, let's try to do the next one completely visualizing it in our head. 7 pi over 6. If you're not sure what 7 pi over 6 is, then break it down and think of it as pi over 6. And then multiply by 7 after. What is pi over 6 in degrees? Yep.
30.
It's 30. So this is really 30 times 7, which is how much? Yep. 210 degrees. So now imagine the circle. Visualize, I usually visualize where 180 is, and then 210 is a little past that. So what quadrant would 210 be in? Yep. 3, right? 210 is in quadrant 3. And then ask yourself where. Is 210 going to be closer to 180, closer to 270, or is it right in the middle? Yep. It's closer to 180. Right? 210 is closer to 180. So if you need a picture, you're looking at right here. That's 210. Is that triangle the 45-45 or the 30-60? Yeah. That's the 30-60. So you've got a long and you've got a short side. What is going to be the coordinate for 210 degrees, which is 7 pi over 6? Yep.
Negative 1/2. Wait, is that 1?
I like the negative.
Negative.
We'll leave it at that. I like that. That's good. But what? Yeah.
Negative 2 squared over 2.
Okay, a couple things. So first, I think you're thinking of a 45, 90, and it's square root, not squared. But yeah, you're thinking of the 45, 90, which we are going to do another one with that, but not this one. Yep.
Negative root 3 over 2 negative 1 over 2.
Right. So it's negative, negative. It's root 3 over 2 because the long side is on the x-axis. The short side is what goes up and down. So that's the y. Okay. And now, we didn't even really need the whole coordinate, we just need the sign. But it's good to practice writing the coordinate. What's the sine of 7 pi over 6? Yep.
Is it -1/2?
Negative 1/2. Yep. So again, if you stopped me in the hallway and said, "What's the sine of 7 pi over 6?" Would I be able to do it in like 1/10 of a second? No, probably not. But could I take maybe 4 seconds and be like -1/2? Yeah. I just have to think about it for a second. Are there some that I memorized? Yeah, like the 30, 60s, and 45s all in the first quadrant. Those I know. And that's how I can do the other ones fast. So you got that one. Let's see, do I have another one? Oh yeah, I got cosine and tangent. Let's do those two. What's the cosine of 7 pi over 6? Yep.
Negative root 3 over 2.
Negative root 3 over 2. And then the tangent, that's where you're dividing the two that you have. So first of all, negative divided by negative is gone. And what else is going to cancel when you divide? Yep, the 2's. So all you're going to be left with is a 1 in the top and a root 3 in the bottom, which is an okay first step. But what would that turn into once we fix it? Yep. Root 3 over 3. Okay. Any question on that one? All right, so we've done a 45 in quadrant 2. We did a 30-60 in quadrant 3. Let's do one in quadrant 4. Do you want to do a 30-60 problem in quadrant 4 or a 45? Preference? Yeah?
This is a 30-60.
A 30-60? 30-60 is a little harder because then you got to think about the numbers more. You can't just write root 2 over 2, root 2 over 2. Okay. So let's just do one trig function. Let's do the tangent. Tangent of 330 degrees. Okay, so think about 330. I already said it's in quadrant 4, so you know that. Is it closer to the x-axis, closer to the y-axis, or is 330 right in the middle? Yeah. Closer to the x. It's pretty close to making a full revolution. Because it is closer to something, it is not a 45-45. 45-45 would be in the middle. So what's going to be my coordinate for 330 degrees? Yeah.
3 square root of 2.
You say that again?
Square root 3 over 2.
Yep, square root 3 over 2.
Negative 1/2.
-1/2. Okay. And now I'm looking for my tangent. So that's y divided by x. And we've seen that pattern come up before. 2's are gone. And when you reduce that and simplify it, what would you get for a final answer? Yep.
Negative square root 3 over 3.
Over 3. Yep. Because it would be negative 1 over the square root of 3, and then you multiply top and bottom, and it's negative root 3 over 3. Okay, so we've done practice in each quadrant. I did not do all 12 points, because it takes a while to do all 12, and if you did all 6 for every one of them, that's a lot.
That's
72.
Yeah.
So,
So does anybody have any other questions on how you find the coordinate for any multiple of a 30, 60, or 45 on the unit circle? So what do you do if I give you something like the tangent of 12 degrees? Well, that's not a multiple of 30 or 45. We plug it in. Okay, we use the calculator. Now I said technically on the unit circle you can also do multiples of 15. It's going to be a little while before we learn how to do the 15 and the 75. So the points that you know in quadrant 1, they're not equally spaced. You've got a 45, a 30, and a 60. That's what it kind of looks like. What you're missing, there's a gap there. That would be the 15. And the gap up here would be the 75. We can do the red ones in each quadrant once we learn a certain trig identity. That comes in a later chapter. But even once we learn that identity, there's still going to be some that we can't do. Right? 12.3 degrees is not something we would ever do on the unit circle. So we use the calculator. Generally, when you are using the calculator, they'll ask you to round. And once we use the calculator, it's very important we set the mode first. So I don't know, this isn't something I don't think we've done yet. When you press mode, on the fourth option down, there's two different things, radians and degrees. The calculator can do either one. What mode you set yours to depends on the question. Looking at that first question, what mode are they asking me to put the calculator in? Yeah, degrees. How do you know that? Right, there's the little circle on the 42. Okay. If I did not see that circle and it said find the 6 trig functions of 42, I would assume it's radians. So we're going to type in all 6. So we've got the sine of 42. And it does say degrees at the top. So you always know what mode you're in, even if you don't go to that screen to check. Cosine of 42. Tangent of 42. So try typing them in. If you're not getting those answers, maybe you're in the wrong mode or you're putting something in wrong. But those should be the answers you get. Now, it said all 6. That's not all 6. That's only 3. To find the cosecant, the secant, and the cotangent, we're going to do it exactly the same way we've been doing it. What do we do with, actually, you know what, let's put all my answers to this. What do we do with each one of those answers to get the other 3 answers? Yeah.
We need to determine the fractions, right?
Can you be more specific?
If we determine the fractions, then we can do then we can divide or have them.
Yeah.
Didn't she say yesterday we can put all of them to the first degree?
Yeah, what does that really do to it? So what does raising that to the -1 do?
Oh, it flips it.
It flips it. So to find the other 3 trig functions, flip all of those. Okay. How do you flip them? Well, you can raise it to the -1. So you could do sine of 42 raised to the -1 like that. That flips it. Or you can do 1 divided by the sine of 42. That's how you find the answers. How am I going to get the secant? What would I type in to get that one? Yep.
1 divided by the cosine of 42.
1 divided by the cosine of 42. There's your secant. And how would I get my cotangent? Yep.
1 divided by the tangent of 42.
1 divided by the tangent. I would just type it in as 1 divided by. That's how I would do it. Okay, so here's your first three functions, sine, cosine, tangent. And that's cosecant, secant, cotangent. And it did say round to 2 decimal places, so 0.67, 0.74, 0.90, 1.49, 1.35, 1.11. What I wouldn't do to type it in, I would not do 1 divided by 0.6 or 1 divided by 0.67. That's finding an answer, rounding it, and then using the rounded answer, and then rounding again. We don't want to round more than once if we can avoid it in a problem. So that's how I would find the cosecant, secant, and cotangent. That is an exact calculation that we can round at the end. All right, let's try that one. Let's try looking at the 6. Do they want all 6? No, I only want 2. Sine, cosine. Okay. What's the first thing I need to do on my calculator to evaluate those 2? Yeah. Right, I have to change to radians, okay? Because that 10 doesn't have a degree symbol. Other than that, everything's the same. Sine of 10, cosine of 10. There you go. Okay, so negative 0.54, negative 0.84. Yes?
How do you know when to change from like radians to degrees?
So you have to look at the problem and look at the angle they give you. If the angle is in degrees, you put it in degrees. If it's in radians, you put the calculator in radians. And if there's no little circle above the number, then you know it's a degree. Yeah, if there's no circle, you know it's a radian. If there is a circle, it's a degree. Any question on that? So this, especially this last problem we did, right before that one, the idea of taking a trig function and flipping it to get an answer, that not only works for 42 degrees, it would work for any degrees. 47, 98, 136.4. It works all of the time. And does anybody remember what you call a formula that works all of the time? Not a theorem, but something that begins with an I. That's what these are called, like sine and 1 over sine. They're called reciprocal, something beginning with an I. No, not inverse. I think a good guess, but yeah. Identities, yes. Those are called reciprocal identities. So the idea of flipping something to get something else and having it work all of the time, not just some of the time, that's called an identity. And the 3 reciprocal identities that we've looked at so far are flipping sine to get cosecant, flipping cosine to get secant, and flipping tangent to get cotangent. Now, there's 6 equations on the board, but there are really only 3 different ones. Think of writing like distance equals rate times time. What does rate equal?
Distance over time.
Distance over time. Then what does time equal?
Distance over rate.
Distance over rate. These, they look a little different, but they are the same thing, right? All you've done is you've switched what was by itself with what was in the bottom. And that's how you got the other one. Well, look at these first 2. If you switch what's by itself and what's in the bottom, you get exactly the other one. So there's 6 equations, but there's really repeats in there. What I'm trying to emphasize by repeating them is the connection. If you flip sine, you get cosecant. If you flip cosecant, you get sine. If you flip cosine, you get secant. If you flip secant, you get cosine. Just goes back and forth. Flip tangent, you get cotangent. Flip cotangent, you go back to tangent. So those are called reciprocal identities. Does anybody have those identities? And again, the three on the left, that's all you really need. Okay. All right. So I told you when we were looking at trig functions, there were undefined comes up sometimes. But I told you there were two trig functions where undefined never comes up. And that was, I don't know if we did any undefineds today. I think that was one yesterday. That was sine and cosine. Okay. Let's look at tangent. Okay, let me show you what tangent looks like. And I want you to kind of get an idea of why there are undefined values in tangent. Tangent has something in it that we've talked about before. It has lots of them. And it's because we have these, it causes undefined values. Does anybody see what we have lots of in the tangent function? Yeah?
Infinities or
Okay, we have something going to infinity and negative infinity.
asymptotes?
We have asymptotes. There's tons of asymptotes, and they occur very regularly. In fact, they occur every other multiple of 90. You get an asymptote. So that's why if you go to your table and you try to type in like pi over 2, you get an error because that's 90 and that's an asymptote. I had to type pi over 2 because I'm in radians. If I was in degrees, I could have typed 90. Now compare that to the graph of sine. Are there any vertical asymptotes in that red graph?
No.
No, it's a wave. Okay. Cosine looks very similar to that red one.
Just something else.
Shifted.
Just a little bit of a shift. It's a horizontal shift. But the point is, when you draw sine and cosine, they are connected waves. And because they are connected, and there are no vertical asymptotes, they go left and right forever without any breaks. So the domain is all real numbers. What do you notice about the range? I mean, tangent, it does go to infinity and negative infinity, but sine and cosine don't. Sine and cosine have definite limits. Yep.
From here, at least looks like it remains between -1 and 1.
Right, it remains between -1 and 1, and that's because if you think of the unit circle, think of which trig function is the y. Is that sine or cosine?
That's sine.
Sine. In the unit circle, what is the highest y value you could ever have in a coordinate? Think about, here's your circle. What's the highest you can go in that circle?
1.
1. What's the lowest?
Negative.
-1. Yep. And now think about the x. X is the cosine. Left and right. What's the farthest left that you can go and still stay on that circle?
-1.
-1. What's the farthest right?
1.
1. So because 1 and -1 is the limit to what x and y can be, that has to do with why x and y stays between 1 and -1 in that picture, up and down. Okay, so the range is between -1 and 1. Let's say I wanted to figure that question out. I don't want to have to work with that angle. Does anybody remember what I can do to make that angle an easier number to work with? Yeah?
-360.
Right, I can minus 360 from it. When I minus 360, I get 90. So that's exactly the same as the sine of 90. How about if I had something like this? You don't want to minus 360 from it because it's not degrees. What could you minus from it in radians? And it's the same thing as 360. Yep.
2 pi.
Yeah. So that would be the same as if you minus 2 pi one time. What do you get?
3 pi.
3 pi.
And would be pi, so
Hey.
180 degrees.
I still don't like 3 pi because that's a bigger number. We could subtract 2 pi again. And now we're basically looking for the cosine of pi. How many times can you add and subtract 360, or if you're dealing with radians, 2 pi? How many times are you allowed to do it? Yeah?
As many times as you need to.
Yeah, you can do it as many times as you want. And that's what this property says. If you want to find the sine of any value, you can find the sine of that value plus or minus any multiple of 2 pi. So this number right here is an integer. So I can find the sine of t, or I can find the sine of t plus 2 pi. It'd be the same thing. I could add 4 pi, 6 pi, 8 pi, 10 pi, 12 pi. Or I could subtract 2 pi, subtract 4 pi, subtract 8 pi, 10 pi, 12 pi. I can add or subtract as many copies of 2 pi as I want, and it will not change the original answer. That's what I'm trying to show you right here. In this case, I subtracted copies of 2 pi. But I could have added it as well. Let's look at this one. Tangent of, let's say, negative 13 pi. If I want to make that positive, what's the first angle that you would get to if you add one copy of 2 pi? Tangent of, yep,
Negative 11 pi?
negative 11 pi. Okay, again, I still don't like that one because it's negative. So I could add another copy of 2 pi, and I would be at which angle that's getting closer to being positive? Yep,
Negative 9 pi.
negative 9 pi. I can keep adding or subtracting 2 pi as many times as I want, and the answer will always come out the same. But it has to be a multiple, an integer multiple of 2 pi. You can't add 2.5 pi. No. You can add 2 pi, you can add 4 pi. You can't add anything in between. Just like you can add 360, you could add 720. You can't add anything in between. It's got to be a full rotation. And the fact that you can do that, that's called the periodic property. So it's a property we've already looked at. I never called it that before. Yeah.
So for the, going back up a little, would the range of sine cosine include negative 1, 1? Or
Yes.
not? Okay, so those
Yep.
would be brackets.
Yeah. Yes, technically you are right with that. That should be a bracket. It absolutely includes negative 1 and 1. Okay, and the last thing. I think I've already said this to you, what an identity is. It's a formula that works all of the time. It's not a formula that works sometimes. Okay, it works all of the time, at least for values that you're allowed to plug in. Okay, we don't deal with like imaginary values being plugged into trig functions, so that wouldn't even be something we ever think about. So I'm going to finish up by giving you a few more identities. You already have all of those written down. Okay, the reciprocal identities. Okay, we just wrote those down like 2 slides ago. Okay, but there's one more group of identities I want to give you. And there's only 2 of them in this group, called the tangent and the cotangent. Can someone remind me, what is sine again? like the definition. It's equal to, yeah,
Y,
y. What's cosine?
X,
X. And what was tangent?
X, Y over X.
Y over X. Well, look at what you can do here. Y is in the top of tangent. What did we just say Y is? Yeah?
Sine.
Sine. And what did we just say X is? Yeah?
Cosine.
Cosine. So what does that line tell you? That last line. Yeah?
Sine divided by cosine is tangent.
Sine divided by cosine is tangent. Yeah. So if you have a crisis one day and your tangent button isn't working on your calculator, you need to know the tangent of 20 degrees. If you don't have a tangent, you can take the sine of 20. You can divide by the cosine of 20. And that comes out exactly the same as the, am I in?
You forgot the division sign.
I forgot that.
And you're also in radians.
Yeah, that's okay, I'm in radians. But you do need the divide sign. So if you take the sine of 20 and you divide by the cosine of 20, it's exactly the same as the tangent of 20. Well, if sine divided by cosine gives you tangent, then flipping it would also work. Cosine divided by sine would give you cotangent. So let me show you how we're going to use that identity to do our last question. There is one more group under fundamental identities. I don't want to do them today. Okay, they're called the Pythagorean identities, but they're not on the test, and we talk about them a lot more later on. Does everybody have those? Okay. So let's look at what we're going to do. Simplify. Cosecant times tangent. The trick to simplify that is to look at the previous page and basically substitute in for cosecant and tangent something else. Write each of these a different way. Start with cosecant. What is a different way that I can write cosecant using an identity from the previous page? Yeah.
1 over sine.
1 divided by sine. Okay. What's a different way, it's the last one we just talked about, that we can write tangent? Trying to write it with sines and cosines. That's the hint here. Yep. It's sine over cosine. Now when you multiply straight across there, what's going to happen there is exactly the same thing that would happen here. What happens when you start to multiply straight across? Yep.
You can cross out the sines.
Yep.
And then do 1 over cosine.
You can cross out the sines, and you're left with 1 over cosine. And what's a simpler way to write cosine flipped instead of 1 over cosine? Yeah. Secant. So what did we just do? We took an expression that had 2 different trig functions multiplied together, and we turned it into a single trig function with no operations at all. There's no multiplication, addition, subtraction. That's called simplifying a trig identity. In general, those can get a lot harder, but you're not going to have anything more complicated than that. All right, let's try this one. Secant times cosine. So the trick is use one of the identities that I gave you on the other page to rewrite that. So when you're done, you have all sines and cosines. And the hope is something cancels out. That's already cosine. So you're not going to do anything with that. If you want to make it a fraction, you can. But what about secant? What is another way we can write secant? Yep, Clover. Right, it's 1 over cosine. When you multiply straight across, what's going to happen there?
Yep.
Right, cosines cancel out, and you get an even simpler thing this time. You get a 1. So that means if you had a problem in trig, and it said to multiply the secant times the cosine, a simpler way of saying that is just replacing it with the number 1, because that's always what it's going to come out to. Doesn't matter what you fill in for that angle. It's always going to come out to 1.
How long is both sides are equal? Like if both secant and cosine are equal?
Yeah, it has to be the same theta. It's not a theta 1 and a theta 2. It's theta and theta.
Yeah.
So like secant of 10 times cosine of 10. Secant of 48 times cosine of 48. It's always going to be 1. Yep. And we spend at least another 4 days on that kind of stuff. But just kind of a little introduction to get you to start to think about some stuff in trig. Okay. That is the homework. Okay, most of that's unit circle. And I'm going to give you one trig identity to simplify. I want you to simplify cotangent times sine. So simplify cotangent times sine. Okay, I'll put a list of review topics on the board while you guys are in your next ones. Okay, guys, you can skip 50. I forgot to cross that one out. We didn't talk about 50. It's not on the test.